Welcome back to Integral Calculus. In this video, I want to talk about centroids. You may or may not have come across the vocabulary term of centroid in a previous mathematics course. But let me start, in any event, by defining the centroid as the geometric center of a figure. So whether or not you have heard this vocabulary before, a centroid is something that you have experienced for at least some very simple shapes. If a shape has a lot of symmetry, the centroid of the shape is at the place that you would expect. Right? For a circle, the centroid of the circle is the center point of the circle. For a square, again, horizontally centered, vertically centered, that's where the centroid is. And one more relatively simple geometric shape here is a diamond, which again, horizontally symmetric, vertically symmetric. The centroid is right at the center where you would think it is. The question becomes interesting when you start looking at shapes that do not have that kind of symmetry. All right, so if you have just a blob like this, how do you determine where its center is? And I'll be honest, that blob is a little bit beyond what I want to get into in this course. The tools I'm going to show you will get you there, but I don't want to go through the kind of computation you would have to deal with something that complicated. All right, let me get my head out of the way. And I do want to talk about one other type of figure that you have seen the centroid for before. And this is the one that we're going to base all of our following work in. This is a straight line, or a line segment. It starts over here at point x1, y1, and it ends over here at point x2, y2. The centroid of a line sometimes is referred to as the midpoint. And you have seen the midpoint formula at some point in the past, I am sure. It says that the x-coordinate is x1 plus x2 over 2, and the y-coordinate is y1 plus y2 over 2. What are we doing with that? What I want you to notice, which may or may not have been apparent to you, may or may not have been pointed out when you've studied this at some point in your previous mathematical journey, is what we're doing here is taking the average value. We are averaging the x-coordinates of the 2 points. We are averaging the y-coordinates of the 2 points, and those are the x and y coordinates of our resulting figure. And by taking that rule and running with it, we'll be able to go a good distance with this idea. All right, so let me sketch out some coordinates here. So we've got our nice xy plane, and let's just plot a couple of points. Start with the point 2, 1. Here is the point 2, 3. And negative 1, 2. Negative 4, 0. Negative 2, negative 2. And I don't know. 3, negative 2. All right, so all told, that's what, 6 points? And we can use the same idea of finding the average here to find the centroid of the region. I'm just going to draw a quick curve here to point out that's the order I'm going to consider these points when I'm trying to write everything down, just so that I can make sure I keep everything straight. I'll go ahead and use the letter M to represent the centroid again, even though it's technically not a midpoint. But we want to take all of our x coordinates. So it's going to be -2, -4, -1, 2, 2, and 3. There are 6 of them, so divide by 6 to calculate the average. And then we'll do the same thing with the y coordinates. -2, 0, 2, 3, 1, and -2. Once again, divide by 6 because there are 6 of them. C. Right, add up all of our x coordinates. We actually just get 0. 0 divided by 6 is still 0. Add up all of our y coordinates. We get +2. +2 over 6 is a fraction that reduces to 1/3. So I'm coming up with the centroid of this region is the point 0, 1/3, which is right about there. And yeah, just looking at it visually, that does look to be around about in the middle of all of these points. So it seems like a reasonable way to go. All right, so we're starting to get somewhere. We have the center of a finite collection of points by averaging their coordinates. But what happens when we don't have a finite set of points anymore? What happens when we have a continuous set of points? And for that, I want to remind you of the calculation of a mean value. If you have a function y equals f of x, and you have a couple of points that you care about, say x equals a and x equals b, in theory, in your previous study of calculus, you learned that the average value, I'll denote average value as f with a bar over it, is equal to 1 over b minus a times the integral from a to b of the function f of x dx. All right, if you don't remember having done this, don't worry too much about it. This is one of those topics that in theory is in every first semester calculus course, but in practice is almost always the last thing you're supposed to talk about. And so if you're even a little bit behind schedule in the course, it's the thing that gets cut. So let's go through this as though you've never seen it before. When we calculate the average value, we want to add all of the points together. And what does a summation do? A summation is adding all of the infinitely many points together. Then we want to divide by the number of points that we had. Well, we have infinitely many points, so in theory that would be divide by infinity, but that doesn't make any sense. So instead, we divide over here by b minus a. It's the difference between the two endpoints. That is the length of the interval. The way I like to think about this, we know that this integral is the area under the curve. And we know that the area of a rectangle is length times width. Right here is the length. So we're taking the area, we're dividing by the length, and what we're in essence doing is finding a line here so that we get a rectangle whose width is the average of the function's values. And that is our idea of average for a continuous region. Let me go through a quick example, make sure that you understand how this is supposed to work. If I get my head back out of the way. So let's take the average function f of x equals x squared minus 1 for x in the interval from -2 to +2. All right, well, just following our formula, f bar is going to be 1 over 2 minus -2 times the integral from -2 to +2 of the function x squared minus 1 with respect to x. All right, 2 minus -2 is 2 plus 2, which is 4. And then integrating. The integral of x squared is 1/3 x cubed. The integral of 1 is x, and we'll evaluate that at our limits of integration. Plugging in +2. 2 cubed is 8, so we have 8/3 minus 2. Then subtracting, when we plug in -2, we're going to have -8/3 plus 2. All right, so we have 8/3 minus -8/3, which is 16/3, and we have -2 minus 2, which is -4. All right, 4 is the same thing as 12 over 3, and 16 minus 12 is 4. So we have 1/4 times 4/3. The 4's will cancel out, and we get 1/3. All right, so the average value of this function is 1/3. If I jump over to a graph on Desmos, you can see the same idea playing out here. So I've graphed my function, and you can see in my setup over here, I've only graphed the portion of the function between -2 and +2. And so we get this bit of a curve. Let's move that so that it's not stuck behind my head and I can actually talk about it. There we go. And so at the ends, you have these very tall bits that are very skinny. In the middle, you have this very wide bit that is relatively shallow. So tall and very skinny, wide and very shallow, average out to be nearly at the center, but not quite. So that line gives us kind of geometrically, if you squished down the tall bits and pushed up the bottom bits, where would it flatten out to? All right. So that's our idea of the average value of a function. And with all of this, we should have the tools we need in order to find the centroid of a geometric figure. Let's get back to our notes and take a look at an example of just that. All right. So here I have a triangle formed by the x-axis, the y-axis, and then this line between 0, 4 and 4, 0. If you take some time to figure out that equation, you can find that the equation of this line is just y equals 4 minus x. And before I get into doing any of the calculus, I just want to think about this geometrically. I see right away that this figure is symmetric about the line y equals x. And because it has that symmetry, I have some expectation that the centroid should fall on that line. I don't know where on the line it will fall, but it should fall somewhere on that line. And so if this was a problem on an exam or something like that, I would probably immediately start off with the geometric argument. The centroid is going to appear on the line y equals x. If I can find the x-coordinate of the centroid, the y-coordinate of the centroid will be the exact same numerical value, and I don't have to find the second coordinate. For our purposes in this video, I'm going to go through finding both coordinates anyway. And in fact, I'm going to take the long approach for finding the y-coordinate because I think it's interesting and it's worth spending some time thinking about. All right, let's start in. We want the average value of the x-coordinates. Notationally, I would write that out as x bar. And I know that I'm going to add up a whole bunch of points and then divide by the number of points that I have. And I know because this is continuous, dividing by a whole bunch of points is going to turn into dividing by a constant value that represents the size of this thing, and adding up a whole bunch of points is going to turn into an integral. I can even predict, because the triangle ranges from x equals 0 to x equals 4, what my limits of integration are going to be. But what are the points? How do we get all of those points? Well, obviously I need to know the x-coordinate of the point in question. But if I look at my figure, over here, near x equals 0, there are a lot of points that have that value. Over here at x equals 4, there's literally only one, so it tapers away. One thing that I can use to represent the number of points of a particular value is the height at that point, y of x. And I said I was going to integrate going left to right. Going left to right is dx. And with that, I actually have an integral. I know what the value of y of x is. I know what x is, and I know what dx is. Getting a little bit ahead of myself, what do I divide by? Well, in one dimension, I divided by the length of the line, the distance from one side to the other. The two-dimensional analog of length is area. So I'm just going to assume that that's what we need. I'm going to divide by the area of this figure and see what happens. Now, if the figure was more complicated, I might have to resort to calculus just for figuring the area out. But this figure is fairly straightforward. It's just a triangle. It's a right triangle, and the two legs of the triangle are both 4 units long. So I know that the area of the triangle is 1/2 times the base, which is 4, times the height, which is 4, and 1/2 times 4 times 4 is 8. So my integral, my average value of x, is going to be 1 over 8 times the integral from 0 to 4 of x times 4 minus x dx. I guess I should distribute before I try to do anything else. So it's 4x minus x squared. The integral of 4x is 2x squared. The integral of x squared is 1/3 x cubed. My limits of integration are 0 and 4. Let's see. Plugging in x equals 4. 4 squared is 16. 2 times 16 is 32. 4 cubed is 64. So we have 64 over 3. I could just try to figure out the subtraction from here, but I think it's going to be easier to distribute the 1/8 through at this point. I'm getting ahead of myself. Then I want to subtract off the lower limit of integration. The lower limit of integration is 0, and subtracting 0 doesn't really change anything. I could at this point try to do the subtraction. What is 32 minus 64 over 3? And if I had a calculator that was happy to deal in fractions, that's what I would do. But I don't have such a calculator on me as I'm filming this video. So instead, I'm going to use a nice trick of the distributive property. 1/8 of 32 is 4. 1/8 of 64 is 8. So we have 4 minus 8/3. Well, 4 is the same thing as 12/3, and 12 minus 8 is 4. So the length here is 4/3. If I come back up to where I can see the figure, I can draw in a line at 4/3. It's that line right there. And just looking at it visually, I feel comfortable in saying that about half of the triangle is to the left of that line, and the other half of the triangle is to the right of that line when I'm talking about area. That looks like a reasonable place to put that line. So far, so good. Now from here, the next thing I have to do is figure out the average y value. And I could, as I said before, just go with the symmetry argument. It had better be 4/3 because the triangle is a symmetric triangle. But I want to think about things a little bit differently. And in order to do that, I want to draw this triangle out again. All right, I'm taking the hard way because I want you to see what this looks like. This is a good example for understanding the mechanism, not necessarily a good way of approaching this particular problem, which is something we do entirely too often in mathematics, but I don't really know of any other way of approaching things. All right, so we're still going to take 1/a. We're going to integrate from 0 to 4. Our integral is going to be with respect to x. Right away, that's one of the things that I'm doing here that I probably didn't have to. If I figured out a way to rephrase this whole thing with respect to y, so that I had x as a function of y instead of y as a function of x, I could just integrate with respect to y and everything would work fine. Since that's not what I have to think about things a little bit differently. Instead, I'm going to think about, let's draw a white line like I meant to. I'm going to think about some particular value of x. And for some particular value of x, all of the x values, all of the points that I'm caring about at that very moment, fall on this vertical line. The top of the line is at the point 4 minus x. The bottom of the line is at the point 0. The midpoint of that line is 4 minus x plus 0 over 2, the average value between those points. In this case, that's 2 minus 1/2 x. But for sake of writing down a formula, let me get my head out of the way so you can see what I'm writing down. Let's call that y sub m of x, the midpoint y value with respect to x. So I'm going to take that ym, and then I'm going to multiply that by the number of points that I was looking at here, which is in fact just y. Ym and y are both functions of x, so if I plug those things in, I'll be able to evaluate this integral. It's going to in all be 1/8, the integral from 0 to 4, of 2 minus 1/2 x times 4 minus x dx. And yes, that's an ugly integral, but we can handle it. All right, distributive property. I'm going to have 8. Let's see, I've got minus 2x, and 1/2 times 4 is another minus 2x. All told, that's minus 4x. And then I've got plus 1/2 x squared. Integral of 8 is 8x. Integral of 4x is 2x squared. Integral of 1/2 x squared is 1/6 x cubed. Evaluate when x is 4. We end up with, well, 8 times 4 is 32. 4 squared is 16. 2 times 16 is 32. And 4 cubed is 64. Evaluate at the lower limit. I love it when the lower limit is 0 because then I just get a 0 here and I am very happy. All right, the arithmetic here works out really nicely. 32 minus 32 is 0. 0 minus 0 is 0. 0 plus 64 over 6 is just 64 over 6. So I've got 1/8 times 64 over 6, which is 8 over 6. And that reduces to 4/3, exactly the value that I said it was going to be from the geometric approach. Let's finish this problem up by saying that the centroid is the point 4/3, 4/3. All right, once again, I took the hard way on this problem. There was definitely an easier approach I could have taken by using the argument of symmetry. The last thing I have for this video is one for you to try, and I say this because I want you to think about symmetry. I want you to, first of all, graph y equals 4 minus x squared. Use Desmos or similar software however you would like. I would then like you to find the area of the figure formed below this graph and above the x-axis. And finally, I would like you to locate the centroid of that figure. Use calculus where you need to, avoid calculus where you can. See what you can do with that one, and I'll see you in the next video.